So up to this point, we've sort of talked about bonding as this binary phenomenon where either electrons are shared, which would be covalent type bonds, or they're completely exchanged or donated from one to the other, in which case they're these ionic. In reality, as is the case for any science, nothing is so simple. And in fact, bonding is really just a continuous spectrum, which is illustrated in this figure here. So you can have things that are completely covalent, which would exist over on this far left extreme. And you could have bonds that are sort of semi-ionic, semi-covalent, and everywhere between, until they sort of reach this completely ionic character where electrons are completely donated from one to the other. This middle ground here, where you're somewhere between fully ionic and fully covalent, we call these polar compounds or polar covalent compounds. And all that means is that the two atoms that are bonding together, they have an unequal sharing of the electrons. And so that could be, two very different atoms where maybe the electrons that form that single bond are closer to this atom than they are to this atom. They're still being shared here, and they still form this single bond, but they may unequally be shared, meaning this atom's a little bit greedier and it's going to pull them in a little bit tighter. We'd call this a polar type molecule in this case. So let's do a couple examples of what that looks like. So if we have HCl or hydrochloric acid, we talked a lot about this as a covalent compound. What do we know about this in terms of its periodic trends of these two things? Well, we know this thing is in group 1A and this thing is in group 7A. So that we already know that the things in group 7A are one electron away from being a noble gas configuration. And so in other words, the chlorine atom is going to have a lot stronger draw of electrons towards itself, right? It only needs one more to be considered fully octet happy. Same is true, but opposite with hydrogen, right? It wants to give away its electron. So even though these are two nonmetals and are forming a covalent bond, this electron pair that's being shared between them, it's actually going to lie more strongly towards the chlorine atom, so that it approximates more of an ionic compound. Even though it's not fully donated, it's heavily lying towards the chlorine. And we use this nomenclature here when we're talking about polar compounds like this. We use this little Greek letter delta, so it looks like a little squiggly like that. And we use that to tell us about the partial negative and partial positive characters of the individual atoms. And so if the electrons are not being equally distributed in this molecule, then we'd say that likely it's being pulled this way, which means this would be a little bit more negatively flavored and this would be a little bit more positively flavored. So we'd say that there's partial positive character on this H, this hydrogen, and there's partial negative character on the chlorine atom. That's illustrated in this figure that I've got here, where you can see the partial positive character on the hydrogen here and the partial negative character on the chlorine. You can also see in this representation the electrons are closer to the chlorine. They're not completely donated, but they're closer. And then if we look at what's called an electrostatic image, this is just a computational prediction. Somebody did some math and computed where do the electrons probably lie. We can see that the shape of this thing tells us where the electron density is. And it shows that the electron density is more centered on the chlorine atom here than on the hydrogen atom here. And so you get this sort of cool color, this blue and purple here, that denotes this partial positive character, and you get sort of the hot red and yellow, that denotes more electron density on that N. And so we'd consider HCl, hydrochloric acid, to be a very polar compound, because on the periodic table they're very, very different from each other. The hydrogen really wants to get rid of its electron, the chlorine really wants to gain one. They're not technically a metal and a nonmetal, so this is still a covalent bond. They're still shared, but hardly shared. So on this spectrum up here, this is maybe all the way over here, where we're starting to approach sort of more ionic territory, less so than the completely nonpolar covalent. So a counterexample to that would be like chlorine gas, Cl2, which is what we naturally find chlorine to be on this planet. And so chlorine can share electrons with itself, a pair of electrons right here. And because chlorine is exactly the same element, there can't be any more or less draw one way versus the other. It's equal and opposite pole. So this is a perfect share. So there's an exact sharing of those electrons between these chlorines. And so this is sort of the opposite example, where we'd say this is a nonpolar molecule. There is no partial positive or partial negative character because it's exactly the same atom on both sides of the bond. And so we'd call this nonpolar covalent. If you scroll back to that spectrum that we looked at before, it looked like this, where you had nonpolar on one end, which was covalent, and then you had a fully ionic compound here, and then somewhere in this region you had polar covalent. That was sort of the in-between. And so a completely non-polar covalent bond, there aren't that many of them, and typically they are formed when you have identical atoms bound to each other, because then they're not pulling any more one way or the other. They're pulling in equal and opposite ways. So a final and third example would be something like sodium chloride, where you have a true ionic bond, where in this case the sodium gave up its electron to the chlorine atom to make chloride, and now instead of having any shared electrons between these bonds, the chloride now has all of the electrons, and the sodium had given that one up. And so you can see the electrostatic diagram here is really sort of extreme. And so on that spectrum, this would be out in the purely ionic regime. But I'd say for the vast majority of compounds, they're going to lie somewhere along the spectrum between a purely covalent nonpolar compound and a purely ionic compound. They'll be somewhere on this polarity scale here. So how do we assess, like what tools do we need to assess how polar a bond actually will be?